started talking about was polar coordinates. And obviously there's a lot more to it than what we're going to be able to get to in 1.5 lecture days. But basically we said that when you have polar coordinates, you label points using r and theta rather than x and y. And we went into a good bit of detail about what r and theta meant. Conversion formulas that you can use when you go from polar to rectangular. Are x equals r cosine theta and y equals r sine theta. Those just come from trig definitions. So cosine is like x over r, sine is y over r, and those are just manipulation to those. When you go from rectangular, I'm using the word rectangular, we could also use the word Cartesian. But if I go from rectangular to polar, you can use the conversion formulas where x squared plus y squared is equal to r squared because of the Pythagorean theorem. And then alpha, which is the reference angle for the angle theta, alpha is the inverse tangent of the absolute value of y over x. And so yesterday we talked about how to plot points in polar, how to give like different ways to name the same point in polar. We also gave problems where we would convert points. So if I gave you a point in polar coordinates, we should be able to convert those to rectangular coordinates. And then backward, if I give you a point in rectangular Cartesian coordinates, then we should be able to convert back to polar coordinates. And so that's kind of what we focused on. What I wanted to look a little bit at today is just a couple basic graphs. So there are lots of different graphs in polar, a couple basic graphs and a couple conversions where we're converting equations. And so a lot of what you deal with in Calc 3 with this involves converting equations from x and y to r and theta. And so I do want to talk about that some. But I want to think about first, what does the graph, so if we were to graph, say number one is, let's do r equals 3. If you think about all of the points that you would graph for that, so like think about all the places where r would equal 3, what type of graph do you think that would create?
It'd be a circle.
It'd be a circle. So it would be all of the points where r is 3. R is the distance from the origin or from the pole. And so we all know I cannot draw circles very well, but you get a circle radius 3 where the 3 that I'm labeling is the x and y coordinate, or yeah, the x and y coordinates of those points. But r equals 3 would look like that. Various values of theta would correspond to different points. So like if theta is 0, it would be here. Theta is pi over 4 would be here. Pi over 2 would be up here. Pi, 3 pi over 2, 2 pi. And then if I go like from 2 pi to 4 pi, I would get another trace of that circle. So it's actually not just one trace of the circle. It's like an infinite number of traces of the same circle. So anytime you have r equals a constant, you would get a circle. What if it was r equals -3? So if you had r equals -3,
it would be the same.
Yeah, you'd actually get the same circle because -3 would just mean go in the backward direction. And so now different points would correspond to different angles. So like when theta is pi, you'd actually be over here. When theta is 0, you'd be over here. But other than that, you get the same picture. The only exception to r equals a constant, so r equals a constant is always going to be a circle except when r is 0. If r is 0, you get just the single point, which is the pole, because that's the only point 0 units away from the pole, or 0 units away from the origin. That's called a degenerate circle. That's not just like making fun of it, that's actually the name of it. And so if it's r equals a number, you either get a circle or you get a single point if it's r equals 0. I want to talk real quick about what, number 4, I guess, what theta equals a number would look like. So let's say I wanted to graph theta equals, say, pi over 3. So we're going to graph all of the points where theta is pi over 3, but R could be anything you want. So what would you get if you did that, do you think?
A line.
You'd get a line. And so you get all of the points up here along the angle pi over 3, because that would get you all of the positive r's. You would get 0, and you'd also get all of the points in the opposite direction, because any negative r would put you down there. And so theta equals a number would give you a straight line that passes through the pole, and it would get you both halves of a line, not just one half. Does that make sense? Any questions? Okay, and then number 5 is not really draw the graph, but number 5 is I want you guys to think about this. So give a polar equation of the y-axis. So see if you could come up with a polar equation for the y-axis. So what do we think?
Theta is equal to pi over 2.
Yeah, so theta equals pi over 2 would work. That would get you everything along the y-axis, any angle that lands on the y-axis. So pi over 2, negative pi over 2, 3 pi over 2, 5 pi over 2, all of those would land on the y-axis and will get you the entire thing. Okay, there are lots of other polar graphs that we can do, and they're a lot more complicated in some cases. But what we wanted to talk about right now was r equals a constant and theta equals a constant. I want to talk about a few where the way that you get the graph is by converting to x and y. And so let's say graph, or describe the graph by first converting to Cartesian, meaning x, y. All right, and so number, well, I'm going to leave the directions up there, but number 6, we'll say is x, I'm sorry, not x, r sine theta equals 2. And so if you were to graph that just using r and theta, that would be really challenging to try to figure out what combinations of r and theta make that statement true. Whoops. But in this case, you can convert that to x and y pretty easily. Why is this one real easy to convert to x and y? What's r sine theta the same as? Okay, so back up to the conversion formulas, we know that x is equal to r cosine theta and y is equal to r sine theta. So if we're converting to Cartesian coordinates, we can make this y, whoops, we can make this y equals 2. That would be the Cartesian equation. And then because it's y equals 2, that would be a horizontal line at 2. Does that make sense? Okay, and so when you're doing these, the idea is to try to get something that you know how to convert to show up. So you know that r sine theta is y. You know that r cosine theta is x. You know that x squared plus y squared is the same as r squared. And so if you have something that seems more complicated, so like r equals 2, say, secant of theta, you can graph that by like plotting theta and r, and there's a whole set of different curves that you can talk about with polar coordinates, and we're just not going to go into that because we're out of time today with the course. But if you have one like this, if it's possible to easily convert to Cartesian, you should. And so secant is the same thing as cosine, or I'm sorry, is 1 over cosine. So we can rewrite the equation that way. And then we can multiply by cosine theta. And that gets us that x is equal to 2. And so that's not like what you do every time. It just happens to work here so that you get this expression where you have x equals 2. That means if I were to graph it, it's a vertical line where x is 2. Does that make sense? Everybody good? Okay, so we should be able to do graphs where r is a constant. We should be able to do graphs where x is a constant. We should be able to do graphs where it converts to x equals a constant and y equals a constant. If you have this instead, so let's say you have r equals, say, 6 cosine theta. So this looks about like the last two as far as how complicated the expressions are. It's not that complicated an expression, but why is this one a lot harder than the last two, at least at first? What makes this one worse?
Because r and cosine are on the same side.
Yeah, r and cosine are not on the same side. And so because of that, you're not going to be able to easily manipulate it to get r times cosine theta or r times sine theta. And so, or at least not using the techniques that we were doing on number 6 and 7. So what you do here, or one way to do this, is I could choose to write this. Okay, and so I want you to look closely at what I wrote and think, okay, why, first of all, am I allowed to do what I just did? Like, what did I do? I did not square both sides. What did I do?
You multiplied r to both sides.
Yeah, I multiplied r by on both sides. Does that make sense? Or both sides by r? And okay, so I choose to do that. And the reason I choose to do that is because that gets me 6r cosine theta, which I know is 6x. And then r squared is x squared plus y squared. And now that is a Cartesian equation, but it's hard to graph from that form. So what you can do to get it to graph, or to get it so that we know what the graph looks like, is subtract the 6x over and complete the square, which we've kind of talked about sporadically through the semester. But x squared minus 6x is the beginning of x minus 3 squared. X minus 3 squared is x squared minus 6x and then plus 9. So we're adding in the plus 9. That gets us 0 plus 9 on the right-hand side. The y squared is already a perfect square, so we leave that alone. But now the point is this, the third line up and the second line up are the same as each other. And now x minus 3 squared is equal to 9. Oh, I'm sorry, plus y squared is equal to 9. And so now this is a circle. With center 3, 0 and radius 3. And so a fitting end to the class will be me attempting to draw a circle like that. And for me, that's pretty good. So, all right, that would be 3, that would be 6, that would be 0, this would be up 3, and this would be down 3. And so we get that circle. That's another technique you can use. It obviously doesn't work every time. It works when you have this. And so what happens in Calc 3 is not so much that you want to be able to graph this circle, but sometimes when you're dealing with like r cosine theta in an integral, it'd be a lot easier to deal with x in an integral. Or if you're dealing with x squared plus y squared in an integral, it might be easier to convert to r squared. And so converting with these, that's stuff where you're going to use this type of thing that we're doing in the, probably not the completing the square part, but the rest of that, like the way we're converting, that's something you do use in the calculus part of multivariable calculus. So converting between polar and Cartesian coordinates back and forth, that sometimes makes integrals a lot easier. Okay,